Hey, this is Coffee Compiler Club. Oh, and here's Mark right now. So anything to do with compilers and language runtimes and garbage collection and type systems and compiler IRs and nil and not the nil and everything else, all fair game. Usually I don't have a set agenda. Today I do. You're being recorded live. You'll show up on Twitter within a couple hours these days. It works pretty well now. If you don't like being recorded, bail out. Everyone here is an old hat, heard me say this a dozen times over, so done. So before I start, why don't we just see if anyone has anything they want to say about—
I'm curious about an AA update before we go into the scheduled agenda.
Oh, well, between house shopping and starting to pack and stuff, AA's in a higgledy-piggledy mess where I got to when things blew up on me because we actually found a house and then we actually got an offer accepted. So I was starting to apply the theoretical learnings on the core AA main base and hit something stupid, and I stopped for a second to do something else, yak shaving, and then that got me into something else stupid and yak shaved again. And then we saw a house we really liked, so we had to go get pre-approval. And then my income is very non-standard, so pre-approval was a bitch, and we had to shop around for pre-approval, and we finally got that. And in the meantime, we found a second house we liked even more. So we slapped down an offer and they countered and we countered, and that all took like 24 hours and we're done. And suddenly we're like, fuck. So I'm picking out a bridge loan at an insane rate. So I have two houses, two mortgages, and a bridge loan with stupid money on it. And I have to sell this house I'm sitting in right now in like 2 months, or I'm paying double mortgage at a ridiculous rate. So I am motivated to move and get out. So AA is taking a back seat, and that's where it is.
That sounds like the correct prioritization.
And 2 months from now, I hope to show you a background view overlooking the Pacific Ocean on my mountaintop hillside with my palatial estate.
That's okay. Cameron has saved a screenshot to use as your
There you go. And for all time, we can have my office background as my living room background. Fine. My new living room in 2 months, 3 months.
You need to stop this mortgage thing. That's no fun.
Yes, exactly.
We were mortgage free for, I don't know, a dozen years or more before we sold our last place.
Yeah.
Which is probably more than doubled in the last, less than 6 years since we bought it.
We just talked about my Sunnyvale house doubling in the last 6 years. Yeah. So
we had a mortgage for a couple of years after we moved into our new place, but it's long gone. This no mortgage life is much better.
Okay, good. I'm making more money in the market than mortgage rates. So technically speaking, to maximize my income, I should mortgage myself to the hilt and throw it all in the market.
Yeah, I have a risk-averse wife, so that doesn't work.
There's some risk there, and so I'm balancing, and I'm going to maintain my equity position, which at this point I own 2/3 equity in the Sunnyvale house, and I'll maintain 2/3 equity in the new one when we're all said and done, and we'll swap out the bad temporary mortgage for a standard conforming jumbo, and it'll be back to whatever the rate is at that moment, be 4% or something. Fine. And then that'll be 4% is way less than what I'm making in the market, so I'm all happy. Okay, I'm going to do the do. I'm going to start in on the sea of nodes thing if I can figure out where it went in my pile. I did a link to the slides. I did update the slides within 2 minutes before starting the camera. So in theory, Dropbox has the updated link, and you can get it if by asking again. But I'm going to share the screen and do SSA based. No, sea of nodes. Yeah, sea of nodes. Let's see here. People see that?
Yep.
Let me go shrink some other windows and get my people view more sane. No, come back here. Okay. And a new guy shows up. And I need Ganesh. Ganesh, I need you're still connecting audio. I need Ganesh's email. Hey Ganesh, I need your email. I'm going to send you a private chat, so because you got no audio yet. Okay, yeah. So what is SSA? I'm sorry, what if C is nodes? So this talks about what it is as opposed to how to build. How to build, I went around 2 weeks ago. And of course, we had a giant long discussion last week about C of nodes. So I thought I'd just I'd make slides that were new and not a hodgepodge of 20-year-old slides. So it's been used in the Hotspot JIT for 25 years. It's obviously very fast to build, to optimize, robust, good code quality, and very fast time. Inspiration for some more modern compilers. Always SSA all the time. I say that all the time. And it's graph-based, which we saw last week. And it's intermingled control and data flow, which we'll see a lot more this time around. And the forward button works. There you go. Yeah. So I'm going to touch the data flow side only briefly because we talked about that a lot last week and the week before. So here I'm going to focus in on the transformation between a standard basic block tuple IR and what I'm doing with the graph, because the theory is that you'll understand the same transformation when it comes to control flow. So I have an expression on the far left. I have a first table, which is a set of quads, which have classic IR tuples. There's a name that gets produced on the first column. There's an opcode in the second, and 2 operands in the next 2 columns over. The names that get produced are all color coded. So RX is blue and RY is orange. And I do from that first tuple table to the second one, all I do is I rename RX to be the pointer to the tuple that would define RX. So it's an alpha renaming, but from a virtual register number to a pointer in memory. Yeah. And then the difference between the table of tuples in the second column and the thing on the right is a topological shuffle only. I literally changed no data structures. I just topologically resorted. So the graph on the right is the same as the table in the middle, which is an alpha rename away from the table on the left. And these things are basically tuples in a basic block, except I'm going to drop the basic block in a second here. And I'm hoping this is all understood from the week before. So the nodes have U-step edges, which are required for your semantics. And the edges are ordered because A minus B and B minus A are different. And you need an opcode, which is expressed twice for me, once as a V table, so I can make virtual calls off of it. Once again, as a small integer enum for hash codes only. I mean, some pretty printing uses it some too. There's def use edges for performance. They're not shown in the graph picture because those are not needed for semantic correctness, but I maintain the reverse direction for fast optimizations. I maintain a small dense integer for using bit sets because you have to have a bit set to walk an arbitrary cyclic graph. You have to have a visit bit or you visit forever in an arbitrary cyclic graph, right? Maybe you throw in an extra constant if you're like a pi flavored thing. Maybe you have some semantic analysis fields I'm not showing here. That's sort of what you want to do with your optimizer as opposed to what the IR means. Optimizations. The bulk of them come out of these peepholes. So lots and lots of very simple graph rewrite rules. You peek at a small region of the graph, you rewrite it, you put the neighbors on the work list, you allow the rinse repeat until things quit changing. This gets you probably half of all your gains, and it's provably linear time, and in practice, it's really fast. Each of these things takes something like 50 to 100 clock cycles to run the peepholes. 50 if you're not doing anything, and 100 if you actually did something maybe. And so you can do millions a second, and it's done. I do pessimistic data flow. So this is constant propagation under another name. Classic constant propagation, including control flow, where I know an if test is true or false or whatever. Those are all also done with peepholes. And there's no difference in the peephole analysis that comes out of the two. I do value numbering or common sub-expression elimination with a hash table lookup where I use that small enum for the opcode as part of the hash code, plus the hash of your inputs, which is just their dense integer. Value numbering is just another peephole rule. I hash 2 things into a hash table. I discover they're identical. So then I declare the peephole, surround them both, and I put them together and merge them. Optimistic data flow happens at a whole compilation unit. produces some result which is hopefully better than the pessimistic value. That'll be the starting point for the next round of p-poles, which will take what typically you find constants in dead code, and he'll fold it up that way. And then everything else you do with an optimizer, I'm not talking about, because that's about how to write an optimizer, not about an IR. So inlining and loops and code generation and things like that. Hey, Arthur. Okay. So I'm going to run through a round of p-poles a little more professionally here, and then we'll Q&A for a second, and then I'll go into the control flow stuff. So p-pole rules, I said, is like major part of your gains. And there's a work list, and you use def use edges for your neighbors. Thanks, Ganesh. The work list I've color coded for my nodes. Most of the rules are tied to the opcode, which I use a virtual call in C++ or Java. Constant propagation, another virtual call. Reverse liveness, Hindley-Milner analysis, all virtual calls. Dead code elimination and common subexpression expression elimination are the same for everybody, so there's no virtual call. The people optimization pass does them up front on behalf of every node before he tries to people that node in other ways. And then we're going to demo that just coming up here. So here's my example where I took my expression, except I discovered for whatever reason that y is 0, and I want to fold it up. So looking at my work list, I'm going to pop that store node off the work list, say it's not dead, there's no CSC opportunities. I'm going to call the ideal call, which is my name for the p-pole, which will return me a new node if there's progress being done, and here's the new node you're going to be replaced with, or nothing, null if you're not, and he says nothing to be done here. Carry on. Pop the purple plus, again, no progress, carry on. Pop the red multiply, it's not dead, no CSCs, but multiply has a rule of multiply by 0, which says I should become a 0. In fact, he has a multiply of 2 constants, and he become the constant, which is the same thing here. So I surround the area in question with a p-pole logic that's unrelated to semantics. It's just there to help me understand. I got a new person showed up who I don't recognize the email for. Oh, I bet I do. This is like no pictures. Is this Christine Flood? This will be fun if it is. Hey, Christine, I see your audio. I don't hear anything. Maybe. All right, gotta be Christine Flood. I'm gonna carry. Oh, I lost her again. Boom, boom, in, out. Oh, let's see if she comes around again. Fine.
She's here.
She's here. Oh, so my screen. Oh, I've got the participant screen shrunk. There you are. There you are. Fine. Hi, Christine. So I'm 5 minutes in, and I'm going to carry on, but I can come back around if it makes more sense to people. Arthur also came in late here. Okay, so anyhow, I have a p-pole rule. The p-pole rules for multiply of 0 says, become a 0. So I replace the contents of the red circle there with new contents, which is I just return the 0, and the graph rewrite engine then does the replacement for the edge-to-edge replacement. That's just an edge replacement, bunch of pointer shuffling.
What stops that from doing something silly like 0 times a error is 0, and don't even go down this malformed part?
Yeah, right. So the multiply rule has to decide what to do if one of his arguments is an error. Most of the guys, if they have an error argument, don't touch anything. They just stop. So they'll make no change. Phi node in AA, I've declared errors are okay if I can prove them to be dead. So a phi node will carry on, do his other things. If later that edge becomes dead, he'll delete it and it'll be dead code and the error goes away. And I don't type in dead code. And it's all fine.
Wait, what is error? Is it a special node?
Okay, so this is unrelated to anything I've said so far, and I didn't have a presentation for error. Error is in AA, this is nothing to do with Java. This is how to handle errors in a typing system. So if the AA typing system allows you to have errors as long as I can parse. So they can be semantic errors, not too many syntax errors. There's a recovery limit on syntax errors. Semantic errors I can handle. Okay, if I have a semantic error and I later prove it to be dead, I'm going to allow the program to type as a whole. Command decision, how I want the language to work. Fine. How does that work in AA? Then I have something I've put in the graph that says this is an error. There is an error value, which is what is the final gating decision. For convenience, there's an error node, which is really a constant node. It produces a value. The value is the error value. So this
Okay,
is,
got it. Yeah.
okay. So now all the nodes that do things where they fold up and collapse ask the question about error before they start getting busy and folding up.
Do they propagate error? Like if you try to add error to something, does it propagate further?
Yeah, and then errors, most nodes, error is poisonous and propagates. So there's the fold up rules, the peoples I'm talking about. There's value propagation, which I'm not talking about right here, but operates in the obvious way. I look at my two inputs, I do abstract interpretation. In multiply, if I have multiply of 0 and 5, then I produce a 0. If I have multiply of 0 and error, I produce an error. And the error is poison. I come to a phi function in a minute. Let's cover it when we get into fees in a minute. But the phi can say, I have an error on one arm and I don't care because it's an error on one arm and I'm going to throw it away because it's dead. Or if it's alive, then he propagates the error and it's poisonous and it carries on. But that's error in AA, it's a separate thing. Okay. Yeah, fine. So after I'm done with the replacement, put the neighbors on the list, which if I look, my purple plus goes back on the list as a neighbor, and I carry on, pop purple plus, add of 0 has a rule, same as before, it's identity on the other side. So you replace inside my little people region with the edge that came in for the edge that came out. The graph rewriter does the update and you put your neighbors on the work list and you carry on. The store has nothing to do with nothing, so it makes no progress. You just pop and carry on. The green multiply now does nothing exciting, carries on. The 0 is dead now, and this is done without asking the specials on 0. It's a people rule does it in general. It just says you have no uses. Sorry, have no defs, no uses. I got that right. You have no uses. Delete you. And neighbors on the work list, there are none. If he had a complicated computation that was unused, the input edges would go on the work list because they also could now be dead, and that would roll up dead code. As soon as you discover something's dead, he continuously eats the graph up, killing the dead things as he goes. Fine. Pull last guy off, no progress done, and that's it. You know, that's people rules for just doing like obvious data flow stuff. So things that do back-to-back loads and stores, and things that do adds of zeros and multiplies by constants and adds of constants and you know, addressing mode math where you have shifts or multiplies with adds get shuffled by these rules to hit a canonicalized order so they all collapse in the obvious ways that you expect an optimizer to do. That's all people rules. Okay, so let's look at some control flow here. So control flow is it's embedded in the same graph format, so it looks a little different, but you have a normal control flow graph buried in there. It's just buried a little funny looking, and I'll show you as I go. And the same people rules apply, and again, I have an example for that. The one thing that goes on that seems to bug people the most is that the data nodes lose a place. They don't have a basic block they belong to. And that their placement in the program is inferred by their edges, their use and def edges. So you can recover it with a straightforward graph walk called global code motion, global value number and global code motion paper. You can look that up. The one in Hotspot does that version, except that it pays attention to basic block frequencies that are gathered by the profiling stage earlier. But you just have to have basic block. If you have basic block frequencies, however you got them, the placement algorithm can take advantage of them to put nodes out of high frequency blocks. So basically that's your loop invariant code motion right there. During the analysis phase, the straightforward graph analyses, the people rules don't care about whether you're in or out of the loop, can't tell, and it doesn't matter. It makes no difference if you're in or out of the loop, and it doesn't change what optimization strategies go on there. And that's a funny thing to wrap your head around, but it's as if you immediately loop invariant code hosted things that were invariant for the loop and put them out in the first place. And then mostly what happens in the IR is he says, I can't tell if they're in, so I'm going to pretend they're out and carry on. Occasionally, I do need that placement information for, in particular, specifically only the bulk loop optimizations. I guess in final code gen. So I find a location when right before I do code gen, I build a real CFG deal with my CF nodes ones, and I put nodes in the basic blocks because I'm doing basic block layout as well as scheduling within a basic block. That all happens right before code gen. So the bulk optimizer doesn't care about that part. Okay, so control data peoples, dead code elimination, unreachable code, common sub expression, constant folding of all kinds, load, store, elimination, all done on peoples only, no basic blocks. So let's look at this. We got some control flow start. I have a starting point. I have some if test that picks 3 or 4. It's pretty dull. For this particular program snippet, I'm going to claim it's the start of the universe. So there's a start node and there's a starting basic block, and the two are synonymous. So the little dashed black line just no semantic meaning. It's just me pointing out the equivalence. So start here essentially is the same as the start of basic block 0. It's just another node in the graph. This one happens to have no inputs, some outputs that I haven't seen yet. Has the start opcode, which goes to the peephole rules. What's the peephole rules for start? Well, they're pretty boring. They do nothing. Sometimes in the presentation and in the implementation, I have an end node. That's the moral opposite of start. Sometimes I fold them up together, call it a root node, and it's both the start and the end of the universe. But that's just how you begin or end your entire control flow graph. So then I'm going to look at a basic block split here. So in the basic block, I put temp as a tuple value is the opcode of some inputs, which I'm not showing, and a jump to some other basic block and a fall through otherwise. So the jump is the last instruction of the basic block 0. It has to be because that's the semantic meaning of basic blocks in a control flow graph. The equivalent side on the sea of nodes, I have an if test, an if node. It has a control edge, which is start, and the controlling value, the op, that is the same as the op for the basic block. So that's sort of one-to-one almost structure for structure. Then I have 2 basic blocks that the control flow graph goes to, BB1, BB2. I have 2 nodes, true and false, that gate which one is which, and they're one-to-one. You can think of true or false as the start, the head of BB1 or BB2. Same as start is the head of BB0. Then there's the guts of the blocks. And here, I had some virtual register X0 and X1 on the left for 3 and 4. On the right, they're just free floating nodes. They don't have any basic blocks they belong to because the code motion will sort that out at a later time. For right now, I don't care. And then I have a merging block, BB3, where region is from Franny Otstein Warren paper 30 odd years ago, program region, whatever. It's a funny name that I picked up. It was lingo at the time. It died since then. The region is a merge point as the head of a basic block, BB3. And it takes 2 inputs, one for the true, one for the false, to represent the 2 inputs that flow into BB3. So BB3 actually has 2 inputs flowing into it on the basic block level. Region has 2 inputs flowing through it at the basic block level. There's a phi. And this is phi nodes for SSA. I'm not talking specifically about SSA directly. So I'm just trying to show the correlation here. On the left in the basic block, phis are generally put at the head of your basic block. And there's a tuple for this format, which has RX2, virtual register 2, X2, has a phi merging X0 and X1. The phi in the IR has 3 inputs. So this is where Aaron said last time, phi is a lousy name. Selector is a better name. The selector value is the region that says which control is going to be used to control whether I select the 3 or the 4, and then you have the 2 values you're selecting between. So there's a gating function, like the transistors, a gating function, the 2 things you're gating between. And that's standard SSA in that sense. The presentation in the graph format means I still need an edge and the phi to point to the region. Same as in the basic block format, that phi node is in the basic block 3, which is how he gets which selector dictates which way you pick a 3 or the 4. So in that case, it's semantically, it's structurally the same as well. Same counts of nodes and edges, except all my edges are on this flat graph node instead of in a 2-tiered outer and inner version of things. So that's.
Is region related to save points or?
No relation to save points. Region is the head of a basic block that is merging multiple inputs. A safe point has a debug information dictating the mapping between the graph IR and the Java virtual machine. They're very different. Regions in particular don't carry any debug info.
So how
And
they relate to a fee node, the region node, how it's relating to a fee node?
okay, the region node is the head of the basic block. It is, in this example, it's the same as BB3.
Mhm.
The fee node needs to know what block he belongs to, so he can tell which selector, which value he's selecting between.
Mhm.
So he has a pointer to his block, where other nodes do not.
Mhm. Okay.
And his block is called region. That region could be named BB3 if you like.
Mhm.
And it would be morally equivalent in this case. The regions have a little other, they're not quite semantically equivalent, but they're very close. So for this conversation, it's fine to say it is BB3.
Okay.
And phi needs to know what block he's in to select between. So not all blocks have to have a node at their head. And we'll see that in a minute.
With the 3 and the 4,
Yeah,
there's no connection directly from them to the true or the false
That's
control
correct.
edges.
that's
Okay.
correct. So this goes to the sea of nodes being the C part, where most data nodes have no connection to any basic block. They are placed later in life when it's time to do code emission. Their basic block layout is discovered with a simple graph walk, which
So
is
at
another
this-
talk I'm not doing today, but it's a simple graph walk.
At this stage, they just exist.
They just exist as free floating nodes in the graph.
Mhm.
They have edges that dictate, the inputs and their outputs, which pin them between their defs and their uses. Case of constants, they have no inputs. They could float to the start of the program. If you had an infinite register machine, you could put every constant the program is going to use in some random register and leave it there for the entire program. And that would be fine. In fact, that was some of the Intel's reasoning when they were talking about the Itanium design, was you have so many registers that you could just hoist things infinitely. Pre-compute with super wide issues all be free to pre-compute. And that didn't work out in practice, but
That's what we do in our IR.
yeah, okay.
So every constant is conceptually a virtual register.
Yes, that's a fine place to go. And as far as I'm concerned, as an IR, it's a totally fine place to go.
Well, and because we don't use a stacked machine, it means that constants and real registers are in the same, for lack of a better term, namespace.
Yeah, yeah. For me, the constants is just what is in the register. The node is a register, if you will, and the constant is just what happens to be in it. But they could be, you sort out later where they end up finally, right? They could be at the start of the world for the IR, as far as that's concerned. At the end, you sort it out. Okay. Any more here?
One more question here. So region has 2 control edges to true and false, and the
Yeah.
fee has 2 inputs. If for some reason my region had 3 inputs, my fee would need 3 inputs.
Yes, and I have an example of that later. Region can have any number of inputs, same as a basic block can merge any number of points. And the fees match 1-to-1 inputs, and that's standard SSA. Every control edge into a basic block, all the fees at the head of that block have to have a matching data value that float in along that edge. So that is like, yeah, that's SSA and nothing to do with graph IR. Okay, so let's look at loops, which is just the same as I did before, except the region is going to come first instead of second. And the split, the if comes second instead of first. So I have my horrible program in the middle, which I did last week before, which is just there because it's obnoxious and tiny. I have some starting point. I have a starting basic block. It has zeros for virtual registers, x0 and sum 0, and the appropriate constant on the right to begin with. And then I have the head of the loop, which I throw in a region. Same as BB1 is this head of the loop. Like the while keyword triggers, if you're constructing, the question is construction instead of semantics. The construction is, upon seeing the while keyword, I'm going to insert a loop header. It's basic block on the left, which has some package I haven't seen yet. It's a region on the right with some package I haven't seen yet. I have some uses for them both, which I haven't seen yet. Just 1-to-1, bang, bang. I'm gonna put the fees in now at the head of the loop. Fees in the basic block, merging the back edge and the fallen edge for X and sum. Same as I put fees on the right for X and sum. I label them in practice, of course, I just call it a phi. I don't have a label for X and sum. The fall in purple 0 and the back edge, which hasn't been seen yet for both of them. So is that, I don't have a selector edge from the red sum to the region, but there is, because I didn't want to draw it in the graph because it's just getting complicated. Guess I could throw it in underneath or hide it or something. But there's a selector edge from the sum to the phi. Oh, the other thing about regions here is since they have a one-to-one mapping between the phi inputs and the region inputs, and the phis have an extra input to the region itself, I one base the inputs to the phi nodes, and I one base the inputs to the region. So the regions have a hidden 0 input, which is always null, just to make life convenient. That's an engineering hack. Removes a stupid +1 between things. Okay, rolling through basic block 1, I do the test. I get an if there. There's a one-to-one mapping between the if node and the test at the end of BB1. The less than 10 is just straightforwardly tuple-based renaming. I then I put in the basic block for the tail of the loop, and there's an exit point, which I have my true and my false. Here, the true points to an exit block on the left BB3, which I haven't shown, and false loops back around with a jump to BB1, and the guts of BB2 I haven't filled in yet. So BB2 misses its guts yet. I'm just showing control flow first, make life easier. So you can see there's a loop from the region to the false to the if to the region. They form a closed cycle in the graph IR on the right, and that is a loop. And whenever I do loop optimizations and loop testing things, I have to look for cycles in the graph, but that would be same as looking cycles in a control flow graph. So the morally same algorithm for the same purpose. Okay. Going again, I fill in the guts of BB2, which has just a bunch of adds. I get the same adds on the right with 2 pluses and a 1. And as Cameron already pointed out, the 10 and the 1 as constants, they can be at the start of the program and floated down. So they were written as if they were in the body of the loop, but in the graph IR format, there is no edge on 10 or 1 that says you have to be in the body. There's no way to tell if they're in the body or not. They totally could be hoisted out. If for whatever reason you didn't have a less than 10 as a single machine instruction, you had to have it in a register, you could preload it before the loop. So the IR can't tell if you're loop invariant or you're not unless it follows a cycle. And the other piece of that is every data cycle in the graph has a phi in it. Minimally 1 phi. Might have more, but it has to have at least 1 for the loop head.
So in theory, every loop optimization you can do on basic blocks, you can also do on SSA, because you can just convert SSA to basic block or whatever, and then do it if you need to, right?
Yeah. Most of the cheap and easy loop ops like strength reduction, scalar replacement and the like, I don't need to go into basic block format. Things where I'm cloning whole loop bodies, I want to know if something's in or out. So in the hotspot JIT, there's the loop pass where I discover loop contents. I do and I declare a region to be the head of a loop, and I put a bit tag on them saying, I know would be the head of a loop. And then I'll come up with a loop body, which does the code motion in small, just in the region of the loop, to say that these are all the things that have to be in the loop. And then when I begin cloning, I'll have to patch up edges. Roughly speaking, I'm doing a basic block conversion back and forth at that point without actually doing it. It's messy code because it's messy operation at this point. But it's incrementally doable without having to de-SSA the whole program, do the loop opt, and then re-SSA the whole program. So it's definitely faster to do it incrementally, but morally speaking, I am coming out of SSA form, whacking chunks of code about, and then coming back into SSA form, incrementally on the SSA directly. But it doesn't have like the multiply of 0 and the add of 0 had a convenient cheap format. That one does not. But things like scalar replacement has a cheap version in the graph rewrite rules, and I do it in the graph rewrite rules as peoples.
Makes sense. Thanks.
Yeah, okay. So anyone else before I roll on for this one? So we all come back to
Did you-
everything here.
Did you consider having an explicit loop node?
Yes, and okay, so I cheated and got there without getting there. So a lot of the loops that you show up in Java, you say half of them look like a for while loop and you're all happy. Half of them showed up in nested try-finally clauses, which forced your loop structure to become irreducible. And you had horrifically bad loop structure. And so the sort of better answer was to sort out actual decently nested inside-outside loops like any good C compiler would do by peeling irreducible parts so they became reducible loops, forcing nesting based on block frequency instead of by Java bytecode layout patterns and the like. Like the Java bytecode layout patterns don't necessarily correspond to the actual frequencies you got out of the interpreter, and things that were go-tos in the fucking bytecodes that turn into loops in the graph, but you had other loops floating around that were sort of more official looking. The frequencies come till you're all wrong and you had to go take the go-to loops. So I have a pass where I begin to do things still in the peepholes only, where I restructure loops so that they nest reasonably with their block frequency. So one of the things I don't say in here, but I have in the actual guy, is that region node and those ifs, they all have an execution frequency estimate that came out of the interpreter, or C1 if you're running a pre-C1 pass before C2. And I'll restructure the loops until I get loop structure that's nested according to the frequencies I've been handed. Some of the frequencies I just come from heuristics as well, if I don't have any other things. But if you have any, whatever you do for frequencies, I nest them properly. Okay, at that point, I've already figured out things that could be loops, a lot of them that aren't efficient because there's no while involved at the bytecode level. And I'll tag a region with a bit that says, you're actually a loop head that I want to believe is a loop head. Like the irreducible guys have multiple loop heads for the same loop. I don't like that. That's like bad optimization. So you begin to peel that loop, like rotating the loop bit by bit, shoving things up through regions and fees to get a rotation pattern until you get one entry point. So you partially peel a loop and you get one entry point finally. Now you have a real reducible loop. And I tag that guy, okay, you're the loop head now. So that all happens before I do the big loop hacks, or as part of the big.
You kind of do have it as a flag on the region, which marks that this is a natural loop.
It's a natural loop, right? So then once I tag it as your loop, effectively I have a region loop node. So at some point I went ahead and made a special region node that was a subclass of region node called the loop node, which was a region node that was tagged with loop. So I could do the virtual calls differently. And I can make hard guarantees. Like a natural loop region has exactly two inputs. And the first is the fallen, and the second is the back edge. And I just knew that. So there were a bunch of people who took advantage of that just to speed up the optimizer. But it wasn't semantically meaningful. It was just an engineering hack to get things to run a little quicker. What to do with loops in a graph IR. This is very similar to things you would do on a basic block control flow graph as well. You come along and say, this basic block's the head of a loop, or it's an irreducible loop. I'm going to start cloning basic blocks around until I get a reducible loop. Then I'm going to tag this sucker as the head of a loop, probably have a list of basic blocks that count to the contents of the loop, probably have to do code motion to get rid of things that don't belong in the loop, which I don't have to do in the graph version. And now I have an official set of basic blocks that are in a loop. I have that set in the graph IR on the right. By having the tag bit on the region, that's it. That's all I need. The back edge, everything reachable from the back edge going up those edges is only in the loop. That's the restructuring that starts the loop ops. Okay, I'm going to roll on here and come back. So there's a little summary here. So I have something that starts my control at the beginning of the universe or ends it at the end. I have a region which merges two or more control flow edges, whoever asked. There's the same count of edges on the fee as there are in a region. There is always one control user out of a region. And then there are a bunch of other users like fees, which use the control to dictate something. One of the things you use it for is a fee to say which of your selectors counts. Other users will be people who have bad side effects at your safety checks with control. So load of a null pointer or divide by 0 will use a control input just to dictate that they need to be guarded by this test, which might be hooked up to a region after some optimizations. It definitely starts getting hooked off of an if test. So I have an if test which splits 2 ways with labeling for the 2 different ways. You can have in-way split, I do. So Java table switch, C switch codes, the exception throw, which does an instance of tree lookup, is modeled in the IR as an in-way switch. It has a value token which dictates which of the in-ways to go to. It has a control that says I got here at all. Then it has in outputs, each of which is labeled according to which of the ways you're going to go. So morally, this is what you would do in a basic block setup as well. It's just like one-to-one on that side of things. So there really is a control flow graph embedded in the sea of nodes. I just have it as a set of nodes because it makes life a lot easier for doing control flow optimizations, which I'm about to get into. So you can always trace the CFG outlines. In fact, I have pretty printers that say walk only control flow edges, and so I can get a CFG printed out. CFG nodes, they people like normal. The people work list can't tell, doesn't care that you're a control node or not. He does the same steps, which is, are you dead? Are you some sort of common sub expression? Okay, call your virtual ideal call or your people rule call and see if you do something. So dead code elimination, constant folding work the same. So dead code means you're dead from below. Constant folding often makes you dead from above, which is unreachable, which has a very similar behavior between peoples and control flow. So the people guy can't tell. So I'm going to go roll through peoples on control flow here. And I have my little merge of 3 and 4 with my region, my fees. And I have an op, which I've declared I know is true, which I've put a 1 in, but whatever you do for truthiness and whatever your language spec likes truthiness for. And I have a work list, which has all the nodes on it, both control and data. And rolling along, I pop tail off the work list, which happens to be a fee, which I make no progress on, and say nothing, carry on. Pop the region off, same story, nothing, carry on. 4 and 3, nothing, carry on. Pop off false, and while he's not dead, he has a use. His ideal call, his people rule call says, I know my input has to be an if. The if has a predicate, which is true, which means I am unreachable. So I circled the area in question where I've inspected the graph and said, I can tell that the false is now unreachable. I'm going to replace it with an unreachable constant. So I use X for unreachable, and the C2 code base was X control, same as an AA code base, it's X control. It's the unreachable control. Just like a constant. Semantically, structurally it's like a constant. It's a placeholder that says you can't go here because somebody uses it. The user of it has to clean himself up. I can't clean it up on the spot without expanding the people to include the region directly, which I'm not going to. Instead, region will clean himself up when he gets to it. So after that, I put your neighbors on the work list, which include the region. And I'm done with that people rule. So false became X control. Pop the region. He has an X control input. His ideal call says, wait a second, I have an X control. I can delete this edge. And all the matching fees that go with it, delete their matching edge. Oh, furthermore, I have only 1 input. So if I have only 1 input, I'm now a constant or an identity on the 1 input, just like add of 0 is identity on the other input, multiplied by 1. Just the same way. Semantically, it's a little odd for its control, but empirically or mechanically, it works totally identical. I'm just an identity on the other input. So I become it.
Do you have your control flow nodes in the same work list as data nodes?
Yep. Because
changing one can lead to opportunities in others. Okay.
Yes, they're in the same work list. That's what I'm trying to show here. My work list on my right here. I'll roll all the way back here. Fee region start 1, 3, 4. if they're all in the same work list.
Okay, got it.
Pop, 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 and I'm starting to make progress now with region. And probably I got here in the first place because somebody made progress on op, replacing it from some random computation to a true value. And then I, kept going from there. Okay, so I become the one region, the region gets replaced with the magical true. However, I have to let the phi nodes know which selector got picked. So there is a broken region, not really region, or broken node left behind that says, I am telling all possible phis, I only have one here, but I might have 20, which selector to go pick. In practice, what I do there is I leave the region in the graph, I whack it on the head with changing some edges to say, you've been made a copy of this other value. That's that slot 0, which is otherwise engineering, lets me get rid of an add of 1 or whatever, 1 base. The 0 slot in the region gets tagged with, hey, you're a copy of this thing, which means that you're going to go away as soon as your last use goes away. And every node has an is copy call they can make on it. And other people can ask a question, are you an is copy? If you are, then I should just peek through you and take what you are a copy of. That works for a bunch of people and not just regions here. So carrying on from there, neighbors on the list. Graph looks a little weird because I'm in the middle of reducing some control flow. There's a phi, not really a region, there's a broken thing that's just a placeholder for the phi. So phi can tell. Okay, pull the phi off the work list. It only has one live input on the R, the magical R. It tells the phi, you need to fold up to just this one thing. So the phi looks at it, checks its selector, says, oh, I need to become the 3. I replace myself with a 3, and I put my neighbors on the work list, and I get done. So 3 and 4 went on the work list as neighbors. Everyone else is already on the work list, didn't matter. Carrying on. Pop the 4, it's dead, remove it. Pop the 3, no progress, keep going. Pop the R, it's now dead, remove it. So if there are more phis, that might wait until the last phi came off the work list. Pop the X, it's dead, remove it. I have a half of an if left. I pop my true value. Same question was asked by the false. He asks also, but on the true side, same code, in fact. He comes up with the same answer. Oh, it's true, but not X control. Instead, I'm going to be just the control input identity of the ifs. So I replace it to the start, leaving the if in the graph, but now it's dead. Neighbors on the work list. Carry on, pop the if, it's dead, remove. So the pop guy doesn't care if you're control or your data. If you're dead, you get removed. And he doesn't know, doesn't care, can't tell. Pop the 1, remove. Pop the start, remove. Work list empty, done.
Why doesn't start point to 3 at this point?
Why doesn't start, what now? Start is control. Something points the next portion of the program off the bottom of the graph, points at start, saying this is where the control goes. The result value of the computation, maybe it's a return from function, is off the bottom of the chart, can't see it, points to the 3. That's the result value. The typical exit condition has a control exit saying I got here at all, like infinite loops. If the optimizer hits an infinite loop, you can't get to the control exit. You can't get to the return. It never happens. The optimizer knows it. But usually the optimizer has a return. The return has some data value. So it has 2 inputs. It has a control. I got to the exit, and here's the thing I'm exiting with. So he needs 2 edges. So start is not 3. 3 is just the result of what happens if you get to the bottom of the program.
Sense.
So let me roll backwards here. So the edges that I have right now, you didn't have any question about. There's an exit off the bottom for the green phi. Somebody's using it. There's a control off the bottom of the true side. Somebody's using it. Those 2 edges remain. If you will, I put a giant people rule that said everything in the center except the start node, the 3, and the things that fell off the bottom were in a big ass peephole that all folded away at once, but there was no semantic change. You still have a control user off the bottom. You still have a data user off the bottom.
So it's not that one of these is the call and the other one is the return. One is merely the entry point to this logic and the other is the exit from it.
Yes.
Okay.
And if you're doing whole compilation unit, it's the start and end of the program. It's a.outs, exit back to the OS. And here's my return value. If you're doing a function at a time, that start is the function entry, and there's an exit, which is the function return. But it's the compilation unit in question you're dealing with, whatever that is. It could be a trace. You're doing a trace-based compiler. You have an entry point, you have an exit point. If you have multiple exit points, you could semantically merge them all at the bottom and say, I have a virtual single exit, but it actually refers to many different exits. You have a universal exit to just to bottom and top the graph and make it convenient to start and end. And actually the C2IR, the C of nodes in the actual C2 has multi-exits. Every exit that jumps to the interpreter, that's a separate exit. I gathered all those exits up in a common exit point, which I call root. That's just there to they don't declare themselves unused and get folded up with dead code elimination.
How big is a compilation unit typically?
There's an exponential curve on those. Most of them are fairly small, so hundreds of nodes or less, tens of nodes to hundreds of nodes. You get the random occasional guy that gets 100,000 nodes. The register allocator has a slow n squared curve on it. And so as you get more nodes, his total portion of the compilation time gradually grows. So everything up to here is linear and actually really low constant linear. So parse is kind of slow for fucking complications in the Java bytecodes that make no sense. Fine. Peepholes are like fucking faster than hell, take no time, do most of your optimization. Loop ops eat a chunk, but it's not too bad. It's like 10% or something. It's not a big deal. Register allocation, code selection is like nothing. Code placement is like nothing. You can't measure them. They're too fast. Register allocation is like 30 to 40% unless you got one of these big guys, and that's 50, 60, 70% in the register allocator. And that's because that n squared growth in register allocator. It's slow, but it's definitely there.
Okay, cool.
So looking at this section of graph in the middle, the start node will never move. The 3 node will never move. The tail end of the blue control off the bottom and the green control off the bottom will never move. But I can play it like a movie and walk forward and see that those points never move, but the insides of the graph gradually nom themselves away and disappear. And I'm left with this, where Aaron had a question about what the hell it meant. But it's the same exact question I could have asked at the very start. What the hell does it mean?
Right.
Only things in the middle got removed to optimize, but there's nothing, there's no change in the semantics of the outside of that area.
So that's the point.
And that's the point. Yeah.
And do you think that it's much easier to write this kind of style transformations with garbage collected language like Java versus C, C++?
Garbage collected has nothing to do with it.
Well, I mean, you have to deal with like lifetime management of these nodes, and you need to make sure that you like free them properly. In garbage collected language, if you tie down one of the edges which held the whole thing, like the whole subgraph, now you don't need to do anything. That like it's gone. You cannot access it, and GC will take care of it. In C++, you'll need to arrange that you free it manually.
Okay,
if you do the arena-based stuff that he says, maybe it's also mildly automatic as well.
I started in C++ because there was no Java. There was no garbage collection. So I just did this with arena-based things. So when I decide this if becomes dead here, right here, this step here between here and here, I pull the if up off my work list. I count his output edges at 0. I say you're dead. I throw you, I do the moral free onto your arena. Their arena management has some speed optimization hack where he says, if things are being built and freed in stack fashion, I can reclaim the storage immediately for performance. Otherwise, I just lost it as a whole in the arena. And the next time I copy from one arena to the next, I'll free up the entire prior arena. That's me doing garbage collection in C++ because there was no garbage collector. Now, Graal guys, they said, we have a garbage collector and we're going to JIT knowing there's a garbage collector behind our backs. At that point, yeah, you don't have to do a free here. You can just, let the garbage collector get it.
Still might want to do arena games inside Java.
You might, and in fact, I do for AA because there's some performance hacks to be done, but it's less convenient in some ways and more in others. It's a different story than C++ arenas for sure. Again, if you're doing stack-like behaviors, you get some wins out of it. In the land of Java bytecodes, many of the bytecodes produce identical safety checks back to back to back. And there you can do peephole rules while you're parsing bytecodes where you get a stack-like behavior where you just had a null pointer check put in, you're putting another one in, you put it in, peephole rule it, it's identical to the prior one, it's deleted immediately, it's at the tail end of the arena, so the arena manager just rolls the arena back and you reclaim that storage. It's all L1 cache hits where you screw around with stuff, but you don't have any special optimizations during parsing bytecodes. The normal peepholes are legal, legit, and just work while parsing bytecodes. And they give me the storage came back. So the fact that I bumped an if null pointer, jumped to death and back cost me very, very little. And the next bytecode, then I added something for the bytecode. And the next bytecode bumped and back. And the next bytecode bumped and back and bumped and back and bumped and back. Turns out in practice, that was roughly a 3x or 4x speed up out of the parser, out of the whole optimizer, because the parser ate up all of 50% of the expansion in the IR. Now, if I'm expanding this off C code, you don't have that kind of stuff going on, and it won't necessarily help so much. In AA, I probably won't have so much of this stuff going on either. It probably won't help so much. The expansion of Java bytecodes helped a fair amount. Okay. So I started down doing memory and I ran out of time to build slides. So I'm going to talk about it briefly and then we're out of slides and I'll summarize. We can come back and talk about memory some more here. So in the SSA, I'm doing SSA based memory, which has nothing to do with CF nodes, except that SSA and CF nodes have a nice correlation. So I treat memory like it's a value, like you would treat pi or some string ABC. It's a big value. It's 4 gigs or whatever, 64 gigs, terabytes is a big value. It has lots of internal structure. It's just a value. Start produces it. Call nodes, fee nodes, store nodes, produce and consume it. Loads only consume it. Those are the main kinds of producers and consumers of memory. I don't have any pretty pictures for stuff because I ran out of time for that. But a fee node can merge memory states from 2 different arms, same as a fee node merges 3 and 4 from an if test. Peephole rules work the same. In fact, the fee node rules are unchanged if you have only one live memory input edge, because you only have one live control path. That's your identity on the one. Store and load have some memory specific peepholes that do shit like back-to-back load store elimination, store elimination, and the like. They both support value numbering, common subexpression elimination. So 2 loads of the same thing will always fold up to 1 load. The precision of the analysis is based on your alias information. And it is correct, but perhaps unhappy, to use a single memory value for all memory states in the universe. Makes it very easy to understand and make sure you've got your memory edges threaded through correctly. But the equivalence class aliasing is both much more precise and become directly represented in the graph. And then I have a slide that I was just starting on for equivalence class aliasing. So it's a pretty grotty slide. I'm trying to show some pie charts to break up memory into the whole of memory is the big circle, but it's broken up into these unrelated different parts. Equivalence classes. Things in the same equivalence class always alias. Things in different equivalence classes never alias. And there's no in between. There's no may alias or must alias. It's always or never. So that dichotomy limits what you can do for aliasing, but it means you can directly represent it in the graph, and all your normal graph peephole rules preserve that aliasing without any further effort on your part. You do the obvious thing for load store elimination, you get the same obvious alias correct graph back. Here I show an example where I have a class animal. It has 2 child classes which have some fields. Fields of the different names can never alias. So they're always in different equivalence classes. Animal.legs is different than cat.meow and dog.wag. However, cat legs and dog legs alias because they're going to alias with generic animal legs. So even if I know something's a cat and he has legs, and I know something is a dog and he has legs, I can't do a transformation in case an animal is floating around with legs, because I'll get confused about the aliasing with the animals. Unless animal is abstract and has no animals ever exist. I only have cats and dogs. Then I can say there's a dog legs and a cat legs, and they're different from each other. So I'm hoping people get the kind of clue what happens here. The strength of this is actually shockingly good. This is a well-known result from 20 years ago on robust aliasing. People were doing all kinds of super points to global, points to context sensitive, blah, 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 everything on the planet they could get. The most best effort, extreme effort aliasing for performance was no more than 5% over what you got from equivalence class aliasing, and typically was just the same. So this covers like 99% of your aliasing needs.
So
Is
when
that-
you say they,
Okay,
Yeah,
Arthur
when-
first, but we get two people. I don't know who.
yeah,
Go
when,
on.
when you say always alias, so may alias falls into this category where you cannot prove that they don't alias, so you consider them as aliasing.
Yeah, so
Okay,
maybe
so
you
you
say
basically-
always alias. It's like a may alias. I can't tell. I have to assume they're going to alias.
Yeah, you course in 3 categories into 2 categories with conservative interpretation. Yeah.
Yeah.
And then my question was, is this 5% only true for Java where you have this like object safety, or would it also be true for C++ where you would need to maybe be a little bit more refined?
Yeah, right. So C++ has the fun problem that you can just cheat like your heart's content, and the compiler can play the as if rule on you to its heart content. So if you cheat and the compiler catches you at cheating, you're fucked. By the way, Alan, your camera's on. It's okay, it happens to me too. Just thought you might want to know. You forget. Fine. Yeah, you can do this on C++, C. You end up with a very similar set of rules. The compiler does the same things typically, except when you start to cheat. And then at the point at which you begin cheating, you either, now you do something C++ specific where you decide as a quality of implementation that you'll be smart about it, or you let it slide and then you start doing things that are impossible, and you generate code that's ridiculous. That's incorrect by some meaning. And that's because the language spec says, I threw a cast that changed the type of something, all bets are off. I can now launch the missile, shoot you in the foot, catch fire and burn to the ground. Nothing, I don't have to print a nice error. I don't have to print a good answer. I don't have to print an incorrect that's subtly wrong, but I might also like catch fire and burn to the ground. Like all rules are off.
Makes sense.
Yeah, in C and C++, this is terrible. If you want to read some of how bad it is, go look up pointer provenance and the strict aliasing rules.
Yeah, they're brutal. Yeah. So I haven't done a C compiler this way, so I don't know where, as a quality of implementation, you would stop and say, okay, wait a second, right? I know, like, from the normal semantic ways it works, you're totally fine doing like all field names with different names cannot be aliased. Da, da, da. So here's a brutal one that actually falls under this bad version for this guy. All arrays of doubles alias. Arrays of longs, arrays of doubles don't alias. 2 array doubles alias.
If you can see the allocation, then you can show that they don't.
Okay, so then you get into and I don't have slides here, what do you do when you can tell locally that things don't alias? And the hack here, or the trick here, is if you do a local optimization that says, I can see in this local space, it's okay, and I do a transformation, that transformation will have global impact for which the aliasing rules may not hold outside some scope. And since there's no limit on how far the knowledge of the transformation just did can propagate, you can, in fact, push this like arbitrarily far and suddenly reach a point where it's not true and generate broken code. There are places in the C2 where I tried a couple of these things where I said, I can tell right here locally on the spot that this is not alias to that. And in one program in 1,000, some compilation you died because of that. And so there's a conservative thing put on a bunch of these guys that has a really funny meaning in the C2IR. It's really hard to follow what the hell's going on there. That says something like, you're not a not null, but you have a cast dependent edge and blah, blah, blah. And I can tell, I can only hoist you, get rid of the control edge that prevents hoisting if I can prove some arbitrarily weird condition that sounds strange. And that's because it doesn't fit well in that semantics. What does fit well is if you say locally, I can see that these don't alias, so I want to let them slide by each other or detach their control edges and reattach them. If you immediately follow that with, and this other guy's dead now, I get rid of him. So it's a two-step process to be cheap and safe. Engineering easy and safe, which is you don't alias locally, nuke the guy based on a regular optimization all in one step. But if you do I don't alias locally, so I'm going to let X slide by Y, you have an issue that the graph is now subtly incorrect if the knowledge of not aliasing propagates too far. And that's a non-obvious thing to do. So the precise aliasing game here with the edges is correct as it stands, no matter what you do to the graph. And so it's a mindlessly easy thing. It's all locally correct. I can see locally these things alias, so they don't. If they don't, I can do the thing. If they do, I have to like suffer. And you just hack away people's blindly, you don't care. In the end, you get a correct program out, and it's generally pretty damn good optimized. Occasionally, you'd love to say, oh, I can tell locally. And if you can never let that new thing, you got a new thing, and you can tell locally it's new, and therefore it can't be this other guy that came from somewhere else. If the new thing never merges with the other guy, you're good. And you can declare it a different equivalence class, and now you're safe. But if it merges with the other guy, what you don't know is that on the recursive reentrant, when the same function is called itself recursively, one of the things that's not aliased on this pass comes in as an input from the recursive pass, and now can be confused with the thing you're making on the spot, and you'll get it incorrect. So there are recursive versions of this that are not correct, not obviously, they're unobviously incorrect.
At least for the like double array case for Java, you have an advantage because if you have JIT time information, you can just emit the runtime aliasing checks, and then you can do that at a better quality than like C++ if you don't have PGA or something like that.
What I didn't do in Java JIT, but I did it like H2O and shit, was put in a runtime check that said, these two things don't alias. And therefore I can go to town on them with the alias analysis. I didn't do that in Java, but you could. Yeah.
So would
how did you put in
local
check?
storage be different kind of?
Okay, Aaron first. Sorry.
Oh, sorry, I've got some latency. Is a pointer to thread local storage going to be a different node type than one that is potentially shared with other threads that might have different rules?
I treated thread local storage as the same alias equivalence class games, which meant that if you had two thread pointers and they were trying to point to two different thread local storage things that you exposed away from thread local storage and just brought out, they would alias. They would be like considered the same. It was not exciting in that way. I did nothing exciting for thread local storage. Typically, these things had different names. They're obviously different Java classes. Since the different Java classes, they didn't alias anyhow, you're done. And you didn't share thread local storage on thread A with thread B by lifting it into a global and passing it to B. If you did, then the normal aliasing rules apply, but I claim you're an idiot and I'm going to shoot you anyhow. And the rules were correct, but maybe less optimal than if you said, oh, this is a B thread local, this is an A thread local, I can tell they're not alias. I didn't do that.
I didn't understand the H2O part about doing it manually. So you inserted like array, like comparison.
H2O did code generation.
Oh, okay.
For exporting code across a cluster that was going to be run parallel distributed scale out, and you could do aliasing questions at that level, and then generate.
And that would just be preserved in the compiler. And
it wasn't done. Yeah, it was done at the Java bytecode level,
okay,
not at the JIT to machine code level.
Okay. But you still got the machine code that you wanted by doing it that way.
I could get some improvement in the machine code for the hottest interludes. Yeah, there's some. I don't remember now what the hacks were, but there was something useful coming out of that.
Makes sense.
Sorry, Arthur.
with array examples, did you differentiate x-axis to distinct offsets where you could prove that offsets cannot be the same?
Yeah, those fall into the Oracle model of the aliasing, or the one where I can tell locally. And again, the rule was if I could get rid of you, because I would tell they had constant different offsets, then I would fold it. That was okay. If I couldn't get rid of it, but I could reshuffle things, then that had a danger that we eventually sorted by putting in an extra control edge and an extra funny rule that said this control, I have to be able to validate the test guarding this control. Still looks like the original test that is no longer visible to me because I deleted it because it got optimized away, and it was a non-trivial hack and it made the core optimizer substantially more complicated with very minimal gain. I won't go there again for quite a while with AA. I might eventually get there. I'm not going to go there for a while with AA. See if it's worth it.
Essentially, you rely on the type information and on like field offsets for aliasing properties.
Yeah. The language already gave me perfectly, these never alias between, meow and wags and legs. They're all obviously different. That turns out in practice to cover, like I said, 90, 95, 99% of your performance gains. You can get some clear hacks and wins by doing smaller things, or doing doing what I call the Oracle model, but you get most of it doing this. So places where the Oracle model kicked in and actually had some payment, IP headers or 4-byte IP offsets, people taking the 4 bytes and they're doing shuffling on them, the IPv4, IPv6, where they're doing shuffling on the bytes and shit. And you had to load 0, 1, 2, 3, 4, and you could load the offset test for your least length 4 and skip the others and then load them as bytes and shuffle. There's special optimizers going on in C2 for that kind of a pattern that know that when they're done, they don't end up with the Oracle model. But they're more complicated, basically a giant ass people split over separate rules in order to make that guy go a little better. And like I said, other things, we did it and it wasn't worth it. And it only added, a few extra bits for a lot of complications, a few extra performance wins for a lot of complications. This is, your mileage may vary, but my mileage was pretty clear.
Is there any reason why the textbook shouldn't get rewritten to stop talking about basic blocks and just use CF nodes all the way through?
I thought that when I started this 20, 25, 30 years ago.
Yeah.
Didn't happen, and I didn't push it, so
maybe a few more decades.
Yeah, it wasn't my job to go convince the rest of the world. I had big imposter syndrome back then too. I had no idea that this was going to be the thing that went 25 years and became, one of the most commonly executed compilers on the planet. These days, I think JavaScript compilers beat it out. But probably for a decade or more, it was the most commonly executed compiler on the planet that no one ever knew about.
Yeah, I think in a way, this kind of representation is similar to how compilers transitioned from non-SSA to SSA. On the one hand, it makes it makes things less straightforward and introduce some entry barrier. Yeah, you need to figure out what this SSA means, but it gives you some convenience in writing transforms. I think this kind of floating nodes is in the similar direction. Yeah, it's less straightforward than typical basic block structure. It takes some time to wrap your head around it, but it gives you convenience of writing transforms. And it it didn't pick up to the same level as SSA, where SSA is just the standard. You wouldn't start writing an optimizing compiler if you're not using SSA. But this one, well, maybe. I don't know.
If you took some random person from the forest that didn't know anything about basic blocks, I don't know, they would say this one was more.
Yeah, I'm thinking if you hadn't seen basic blocks, you'd call this one just as better or simpler or whatever.
Well, what I think a person who knows imperative programming, where you write statements one after another, it's more natural to think of programs as sequential things. That's why I think it's more natural at first.
Okay, there is a sequential semantics here. So I threw this slide up because it was just covering the same ground that, easy to write and debug the peepholes because they are peepholes. They're entirely local and they are locally correct. So your rule only looks at your local neighbor and makes a local transformation based on what it sees. And yet, like the swarm intelligence, you get a really nice optimization when you're done. So it's been used by, over the years, hundreds of engineers, at any one point, 10 to 20 actively writing peoples or screwing around. I think now it's probably slowed way down, but you know, you went for a long time, did a lot of stuff with it. This slide was just me summarizing again, you know, what you do with it. You have to walk the graph. You end up walking control and data at the same time. You visit bit. The size is typically, I mean, it's the size of your compilation unit. You basically get a node per interesting program point, and you get an edge count that's a ratio of the nodes typically. You know, it's 1 to 3 edges per node, roughly speaking. So it's roughly order in nodes for order in program. No n squared blow up is what I'm saying. Debugging usually involves pretty prints, but I pretty printed when I was debugging control flow graphs as well. And the pretty printer is, you know, CFG aware, same kind of deal.
With the increasing usage of a functional programming, are there some changes to the CE of nodes that can directly benefit of the functional programming, or it's all there? It doesn't need.
It's unrelated.
Mhm.
At this layer, it's just, you know, functional programming is calls, and now you inline or you don't.
Okay.
Right? There's a semantic value analysis, which says I want to do something like Henley Milner. Is not related to this, really. I do it on an SSA format because I can, but it's not. You can do Henley Milner on whatever you're doing Henley Milner on. It's fine. You
Yeah.
do it on AST, you do whatever. You get your typing out. That's your typing info.
Mhm.
Okay, I represent calls as they take a function pointer argument. That function pointer argument I'm going to do flow analysis on and get a precise, reasonably precise control flow graph, call graph out of that. That analysis is done by AA. C2 does something similar. It doesn't really matter functional or not in that sense. Having a reasonable call graph lets me inline calls as opposed to treat them as a black box node that I don't understand what goes on.
So inlining is the single most impactful optimization for functional programming.
Yeah, I think so. I think that remains true.
Yeah, I believe this is true. Yeah.
Yeah, one question related to the aliasing and also related to Valhalla. So if I have a Valhalla object embedded within like a normal Java object, I cannot modify the individual fields of the Valhalla thingy, but I can modify like that whole thing in one shot. But if I only modify one part of that, so this memory aliasing thing will guarantee that only the one store gets embedded.
Yeah. Right? So that embedded object has the same. So you have levels of approximation or levels of precision you can go to. The one I just described would say the fact that you're embedded or not means nothing. You have a field on the embedded guy. That field does not alias with any other field of any other class of object. Mm-hmm. Right? But two of those guys, one embedded in a this thing and one embedded in a that thing, would still alias. But you could go to another level of precision which says, since this guy's embedded, if I have a pointer to an A with the inline version of an animal, and I have a pointer to a B with an inline version of an animal, A.animal and B.animal represent different equivalence classes, and they'll never alias. But to make that actually work, you can't ever take a pointer to the embedded object and pull up a generic animal out of the embedded version of things. My question was slightly different. So if you only have one object, and I do like a read, modify, write effectively in the the Java code, it would look like I'm doing all those stores, but you would know that it's the same value. So can you guarantee in the compiler using this aliasing that those unnecessary stores won't be emitted? Right. So this gets into what is the precision of the analysis again, and then what do the people roles kind of do? So if you are doing what I heard you say, I was doing a whole object replacement. Yes, because that's the only option I have with the Valhalla thingies, but I'm only changing one thing. Yeah, no, internally the compiler could, and I do, and I don't know where C2 is doing with Valhalla because I left before Valhalla came around. The obvious thing to do is to say, I issue a series of stores, one for every field.
Yep, yep. And then those like the unnecessary ones will just go
And then
away.
yes, and
Yeah,
the peoples will eat up all the unnecessary ones. Yep.
And can you guarantee that that always happens?
I can. I haven't. I don't know if Valhalla will. It can
Mhm.
be done that you can
Mhm.
guarantee that happens.
Mhm.
So what does unnecessary means? It means that you took some, you knew from some other thing that like you said, guarantee. So guarantee turns into basically type analysis, which says, if I can't guarantee it, I'm gonna throw an error at you,
Mhm. Mhm.
right? So what are the rules in which I can guarantee it? Well, what's it mean to be unnecessary?
The Valhalla object is immutable. So if I only do like one thing, I know that all the other stores are unnecessary.
So hang on.
If I'm
So
writing
you
it down.
store into an immutable object. The semantics are you clone the whole object and you store one field.
Yes, yes.
You're
yes.
hoping that that object has a single use, and somebody will come back through and say, don't clone the whole thing, just leave it in place and update in place because there's
Yes,
single
yes,
linear
yes,
use. Okay,
yes, yes.
now you're asking question, can I prove that I only have a single linear use? Because as soon as I have a single linear use, I can do update in place. Now you need a typing system says I have a single linear use, and I'm proving linear logic on it, which is basically like what Rust does. So can you prove it? Yes. Is Valhalla proving it? No.
I'm not sure.
Now you have to prove some kind of linear logic, because if I have this and I have a use of it here coming off going this way and use of it here coming off this way and other uses floating around, and you want to store a field, you're going to make a new object. The compiler is going to have to choose between cloning with an update or an update in place. You know, if you look at Swift, they said we have reference counting now. We pay that, we make it a guarantee that you'll get the incremental update by also requiring reference counting every time you touch that damn thing. So you pay for the reference count and you win by not having, by getting to commonly do, you know, the cheaper store optimization. It's actually what you win on is you don't copy when you can't be sure that a store is coming. You don't copy because the reference counting tells you just bump the reference count. So the you know, reference counting gives you that hard win at a cost. The Rust style semantics gives you the hard win at an engineering of my program, you're writing the code cost. And decide how you want to, or you can not have the hard win and say that statistically speaking, I typically get the win. And as long as it always wins in all my hot code, I don't care if it wins or loses in the cold code.
I think in the Valhalla context, they have introduced the concept of withers. So like not only like they had getters and setters, and now they have conceptually withers. I'm not sure if it's reflected in the bytecode, but I think this it's
basically
mutate
is the same except this one.
Yeah, this concept of I have this immutable value that exists somewhere in some mutable storage space, and I want to update that mutable storage space to a new value that retains some of the old members. I think that's they introduced like withers for that.
I'm not picking up the word.
Withers.
WIA.
Yeah, this is the with field bytecode.
The word with. So basically, you have a constant value. Say it's a point, right? So I say new point 0, 0.
Yeah.
P, and that's P, and then I can say P with X equals 1, or depends on. Depends on
Elm does that.
Right.
Fine.
So it lets you replace a value at a time from a constant and only do an entire copy.
Yeah.
Right.
My desire is even if you have a chain of those withers, if that's inside a single local function, I want to guarantee that only the stores that need to happen.
Yeah, to get that guarantee, you have to add some semantic knowledge that says you have only one user, so I can update in place, kind of thing.
I thought you would get that automatically because it's immutable.
No, somebody else has got a same copy of the same thing, and you're not changing their copy.
Oh, yeah.
Yeah, the challenge is that the compiler can't read your mind. So if the language isn't designed to convey that to the compiler, then the compiler has to do an awful lot of work to prove things like that, if it's possible at all.
Yeah, right.
Makes sense.
Rust demands certain amounts of you handing it knowledge to get that proof done.
And this is why, you know, I love what I love the way they're evolving Java. I think it's as good of a job as could be done, you know, but that said, it's why you want to design immutability into the language to start with and not try to glue it on as an extra feature, because you know, features are exponential in terms of complexity, right? So every time you have to add a feature to fill a hole, you n square the design, right?
Yeah.
And you know, when you get up to n to the n to the n to the n power, you know, trying to fold that into something that you can optimize is really, really complicated. So I mean, they're doing a great job of simplifying, you know, simplifying that exponent as much as they can, but it's still a freaking exponent.
Yeah. Yeah, it gets ugly fast. In the language, like, you know, the optimizer can always shortcut and say, I'm just not going to go there. I'm not going to optimize. But the typing system, the language spec, it has to cover all them.
Because you know,
both sides of
Java already has kind of a couple type systems that they're trying to squeeze into that.
Yeah,
to
right.
start with.
Yes.
And so you know, this just complicates that, right? It used to be you had a switch that said, you know, switch, is it a reference type? Is it a, you know, what you had Boolean, byte, char, short, int, long, float, double. And now you're going to have, you know, now you're going to have some additional things that you have to handle that, you know, kind of act like one and kind of act like the other. So.
Yeah.
It's nice to be able to tell the compiler both constraints, though. Sometimes I'd like to say this is immutable, and sometimes I'd like to say, hey, this should be a unique reference. If it's ever being aliased, let me know I didn't do what I intended to.
But is the alias problem really existing for value types in Java? I think I'm not really seeing it. Like either you get a copy that's independent if you pass it around, or you have some kind of yeah, I mean, you can't really have a direct reference in Java. You can of course have this prototypical syntax of, okay, I have this value type name dot ref, and that means I have this value type value, but I actually only have like a reference to it. Even in that case, it's copied first, as far as I understand.
And Swift is the third option of reference counting. I think that's your kind of stuck in one of those domains. At least that's where we're at now.
One interesting innovation I found in the Valhalla space is that they not only have like the reference space that existed forever and the value space, but they also have this space in between where they say, okay, we have like this value type, but treat it as if it was a reference. So for instance, if I have an array of this value type, treat it as if it were a reference. So you don't have the flattened field inside the array, but you have references, which allows to have nullable value types really, really easily and cheaply, and only benefit from it being a value type if you pass it through registers, and then it's then you don't need to have this indirection through boxing or through references anymore. So that's an interesting detail that I haven't seen before.
I remember hearing about that piece and never sorted out.
Maybe this is a little slightly different topic, but in some of your talks, you talked about the work that you did for register allocation inside of Hotspot.
Yeah.
Can you? I think so that knowledge is not lost. It might be, again, these presentations take a lot of time from you, obviously, but it would be nice if there was something that showed what you are doing that is different from what might be done normally, especially with respect to the frequency-based stuff.
I have unfortunately really old PostScript only files right now. I'm trying to find if I have a PDF version for interference graph building. I did another one. It's actually, I was having trouble finding a PostScript reader, not a PDF reader.
I feel like every time I get a new laptop, I have to download one manually.
Right. Well, I had trouble finding the standard Ghost View guys like bailed out and said, we don't care anymore. We're not doing it. I have a PS files where I did interference graph building. So the short answer was inlining such a critical optimization. You want to inline sort of more freely. Every time you have a function call that you don't inline, you pay prologue and epilogue, get in and out for call or shades. Once you inline, you get more live ranges, which you run out of registers, so you spill, and the spill is morally the replacement for prologue epilogue. What you want to have true as a property of your register allocator is that those two values balance, that they never exceed. That is, if I inlined, nothing happened in the optimizer good, and I had spills, that would be the same behavior as if I didn't inline, I had prologue epilogue code and nothing could happen in the optimizer because it was a different compilation unit. So I want the count of spills I got for inlining to be no worse than the prologue epilogue code. That's the property you're looking for. That property was not in any register allocator I ever dealt with up till I got to Java. And at that time, I looked at a butt ton of them, like 20, like 4 industrial quality big guys. I wrote 4 that I would claim to be industrial quality independent of looking at some other 4 guys. And then I looked at a half a dozen other people's things everywhere. And always the rule was like a Lay's potato chip, one good spill deserves another. Once you started spilling, boy, you spilled and you spilled and you spilled and you spilled. And you quickly spilled more than the prologue epilogue code, which meant that you're better off not inlining, which meant that you went into the inlining heuristics and you dialed them back, which meant in C code, not a whole lot, but in land of functional programming and Java, even at that era, you lost inlining opportunities that you should have taken because they would have paid off, because you're desperately trying to avoid over inlining and then dying the register allocator death, where adding one more inline caused so much spill code that your total performance fell to the toilet. It just drops off a cliff. So there really was a performance cliff. You'd add inlining and performance just grow until it just sank like a stone. It was ugly. So I worked really hard in the allocator for Hotspot to have that graceful roll off. As you added more and more inlining in the live count, and you got 15 registers, actually live counts, I have 10 live things, oh, it's easy. 20 live things, a little spilling. 100 live things, ooh, a lot of spilling. Okay, thousands of live things would happen, totally. Like, what the hell? Some machine generated piece of code unrolled hugely, and you just said thousands of live things. Holy fuck, what the hell? You could do something and make it not be spill after spill after spill after spill. And I did that, and that was a major payoff for Hotspot that let me turn the inliner back on, basically.
Yep. One more related question is I think Zing allows you to save the profiling info for one run and then reuse it in another. If the code changes, how do you represent that profiling information such that you can use fragments of it for the new run?
That's
or like in general, how would you do that?
Yeah, that's an Arthur question. I have a guess. I think Arthur said it though before.
Yeah, we save information. So there is some fuzzy matching, but basically we save information attached to bytecodes. And if for classes and methods where we cannot match the profile, we just don't use the saved profile. So it has some tolerance to changes, but in the worst case, we are only feeding a profile. So that profile shouldn't lead to incorrect behavior. It would lead to worse performance. But then it's your mistake of trying to reuse old profile where you rewrote things significantly.
Do you still put in the new counters for the first phase, even if you reuse a new profile or reuse an old profile to catch if you got it wrong?
Do you mean whether we collect the profile even if we had profile earlier?
Tiered compilation, you run some profiling also before
So
you.
we would try to pre-compute eagerly, and if we had an opportunity to pre-compile eagerly, if we pre-compile eagerly, we will not fix the profile. We will not have an opportunity to collect the new profile. We would reuse the old one. But
Okay.
if there was a deopt event, we would mark this and we would save this for later runs as well.
But you you gather, if you have a deopt event, you would then be gathering profiles, at least in the interpreter.
Yeah, for some of the deopts, we would be updating the profiles.
Do you ever run a tiered compilation? You got to.
Yeah.
Okay. Is the tiered C1 versus LLVM, or is it all?
Yep.
Okay.
C1 and LLVM.
Yeah. I did the C1, C2 integration. So C1 collects, and C1 can collect profiles like 10 times faster than the interpreter can collect profiles, but it's still substantially slower than your pass two. Right.
Yep.
I put a wither example up on the document if you want to take.
Excellent. Wither, God, never heard that. Maybe
So it's just a method called with on an immutable object, right? So you create the immutable object, which means you have to give it all the data up front. So that's a shorthand constructor after the class name, short form constructor. And then the with just takes optional parameters for all the fields, and all the non-null ones, it replaces the this value with the non-null parameter.
Not the syntax I would have chosen, but I understand what's going on.
I think it's not even. I don't think it exists as a syntax or as a language feature. I'm not even sure if it ever will be. I think it exists conceptually, and I'm not even sure if it exists in the bytecode already or ever will. But it's at this level, so it's
well, syntactic sugar. No, it's not even syntactic sugar. It's just a function call. You're saying like the compiler takes a clue or something.
Valhalla has a new bytecode for it. There's a with field bytecode.
Oh, really?
Yes.
Yeah. And basically, if you have a value, the value type which is immutable, but it's in a mutable storage space, you can say like value type dot some field equals something, and that will end up as a wither in the bytecode.
Right.
The short version of wither is
clone this object and then change one field, but be efficient.
Oh, that's the common functional approach. You copy, but just one object you change, just one field you change, just one field.
Right. Clone some immutable object and make a new immutable object with the one field change, and now be efficient.
Okay.
Which, if I can prove something, I update in place. And if I can't, there was a copy. And if you do field by field copy, as Ganesh was asking, yeah, the people optimizer cleans up all your extra peoples, all your extra stores. Certainly, like in the land of allocating new objects, the runtime guarantees me everything's going to be pre-zeroed because I need to have a hard race condition ordering of the zeroing before you publish an object, but you promptly initialize all these fields with stores. And so the compiler always, for new objects, always had an optimization where it said, I'm overriding, don't put the zero store in, or I know I had a zero already, so the second zero store can go away, or whatever. We optimized the initialization of an object with its escape into the greater Java domain, cross-thread domain. And that was just back-to-back stores or peepholes that said, I have a new and a store, I can do something, the thing.
We played games for a while with TLHs or Threadlocal heaps where we had a zeroed one and a non-zeroed one. The JIT could then pick which one it wanted, but it tended
that version.
It tended to lose because of the locality issues. You had objects that really wanted to be close together, ended up being separate in separate TLHs.
Right. Yeah, that makes sense. Like at Sun, I played games with pre-zeroing lesser or greater amounts, but if you pre-zero large pages, it just flushed your L3 and then reloaded it back in. So if you zeroed small amounts in your L1 or your L2, it was a little cheaper, but if you didn't zero at all, the optimizer could get rid of half of your zeroing rights because you weren't using mem0. The mem0 didn't help. The string zero instructions weren't helpful compared to just issuing stores if you could get rid of some of the store zeros or whatever. Then in Azul, we had custom hardware for doing zero cache line zeroing. It was always a win to use.
Yeah, we still have pre-zeroing. We experimented with explicit zeroing, relying on later on compiler optimizations. Like it gives wins in some cases, it loses in other cases. There's no clear.
That was my experience. It wasn't a big. You got way more fun out of doing correct kind of inlining or loop optimizations than screwing around with news. It looked like something you could do, but it didn't ever left or right. Yeah, fine.
Yep. There was so in some of the previous meetings, there was some talk about hash tables, and there's posted a link in the Google Doc. So once you have SIMD instructions, it kind of changes the calculus a little bit about linear probing versus other approaches, because you can search many more of these. Like if you store the 1 byte hash metadata, you can like do many comparisons in like a single shot. So it wins more to do linear probing than you might otherwise think.
So the game with the hashing that we talked about when Jonathan Blow was here was basically if your reprobe was convergent versus divergent, then a bad hash started giving you long linear chains in a row. That's what you wanted to avoid. But the thing that I first started working with was reprobe of 1, which is not divergent, it's convergent, because I would get several hits in my L1 cache in a row. So I could check a bunch of things after the cost of getting one L1 in. I can now probe 4 things in a row before I ran out of L1 cache, which is what you're talking about in your SIMD. So the blend between the two would be grab things, cache line at a shot, SIMD, check as many things as you can for your keys, and then do a divergent probe for the next cache line if your hash function sucks. So you want to do, I think you want to do a little of both.
Mm.
And analyzing your hash function. If you have a high frequency, high use hash function, analyzing the hash quality is worth it. There's some big numbers that can be stupidly bad or just fine that you can't tell without profiling.
There's some like hardware software interplay where you can like manually insert the prefetch, but it will get nullified if it's like high memory bandwidth kind of situation.
No, hardware guys hate that.
Yeah. Okay.
You can't nullify the prefetch. It's fire and forget from the CPU's point of view.
Nullify as in it won't actually do it if it's high memory.
You didn't issue it. You don't want to do it, you don't issue the prefetch. But if you don't issue it, then it didn't get out there fast enough.
No. Even if it issues, you can nullify it. At
yeah,
like
but then the hardware guys hate that because then you're chasing something. Bits went out the wire to the next layer in the hardware hierarchy. Somebody else's problem. Some other bits are chasing after it, trying to catch up to it.
Not chasing after it, right? So
you're talking physics now. We're not talking software.
No. So there's nothing. So once you issue the prefetch to the L2, I'm not talking about something going again to the L2. The L2 would know from the memory controller getting feedback that whether it's high memory bandwidth utilization or not. So it's not, you're not chasing the thing.
Wait, that's not what I heard you say then. So somewhere somebody issues from this core to the L2 a prefetch that says go fetch a line to the memory controller.
Yes. And then that L2 either decides to do it or not do it based on the memory bandwidth utilization.
Okay. Yeah, okay, fine. That's another one where I claim you want to be a hardware guy and have the billion instruction traces in front of you.
Mm-hmm. Yeah.
Because sometimes it's still a win and sometimes it's not, and you blow off the prefetch promptly, the CPU core stalls for the entire memory latency waiting for it. That's a big stall, right?
You can even have like different kind of prefetches that wait at the L2 for a little bit, so you can do the catch up if necessary, and then that's like
then it got complicated. It's already super complicated, and it's all done at transistors. You're writing transistors here. You're not writing a program.
Yeah.
And the hardware guys hate you.
Yeah.
I have been down that path because I sat next to the hardware guys and we talked about all these kinds of crappy things.
The latest optimizations of the XS hash exceed the sequential round rates, clocking out 29 gigabytes a second to 31. I will throw a link.
So what, I'm sorry, say it again.
They exceed the sequential round reads the speeds of the SSA hash versions of the XX hash. And it reads 29 gigabytes a second and 31.
What's XX hash? I'm missing something here.
Yeah, it's a hash function. We're talking about the hash, and it's pretty far exceeds the even the reads of the RAM it's capable. So.
Oh, I see. Okay. This is the next version of Hashtable games.
So.
You get hash tables that sit in your L1. What are you doing with them? You're reading them so fast that you don't go to main memory. And maybe at that point, go to a perfect hash and constant set of clock cycles and be done.
What hardware games ended up being worthwhile in the end? You talked about like the zero cache line.
Yeah, that was a big one.
Talked a little bit about
that was probably the largest win. Another interesting win was x86 has gone far down the path of having super large caches for its fast cores. Dialing back the size of your caches by powers of 2 only loses you some small percentage performance gain. The problem is that people don't know how to code for multi-core. So x86 was experimenting with 2 cores when Azul had 24, but they had tinier caches. But if we quadrupled the size of our caches, the cores wouldn't pick up hardly anything. They would pick up 5%. So we decided to have 4 times as many cores instead of 5% faster cores.
Maybe that's because you were looking at Java programs that are like pointer GC anyway.
Yeah, we were looking for people who were doing big web servers for big business logic, big web servers.
Yeah, but if you were doing like
parallel work,
plus custom cache blocking kind of thing, then maybe.
No. As soon as you play the game where I have a well-structured, well-understood memory access pattern and high inherent built-in parallelism, this would also win. You have to screw around a little differently, but you get way more flops. We had hugely more flops than an x86 did, and hugely more bandwidth than an x86 did. So the equivalent box from Azul would have the equivalent horsepower of 100 x86s. Right, so just that we had way more cores. This is like with Ludicrous. So we had 800 cores versus 100. The 800 was equal to the 100, right? But we could have that when you couldn't get 100 on the x86. No way. So we actually sold some to the big labs because we had fucking bandwidth for days, and people doing structured block computations could get like ludicrous performance numbers out, supercomputer performance numbers out. We were in the top 500 type 50 supercomputers for a couple of years for bandwidth. It was ludicrous bandwidth.
Just posted a link. The latest chips I've been looking at are now 768 meg of cache. So basically a gig of cache on a machine that probably has either 16 or 32 gigs of memory.
Yes.
Maybe more like a terabyte.
Say again? Maybe
quite a bit more than 16 or 32.
No, because so use cases again. The typical user of this is playing a game.
Yeah.
Oh, you're talking on the like the desktop side. Yeah, then 16 or 32 makes sense.
Oh, interesting. I didn't realize there was AMD.
It's the AMD. It's basically 3D memory used as cache layered on top of an EPYC chip. So it gives them about a 12% up boost, if I remember correctly, on IPC by tripling from a 256 meg cache to a 768 meg cache. But I mean, that's an impressive, it's basically what video cards have done over the past few years, which is instead of having memory, they just stack cache to 24 gig of cache called HBM.
Separate process or the same die? Same die or different die?
So it's a different process, but it's the same die.
Oh, wait, really?
You just heard that right. So basically they're layering chip on top of chip.
Interesting.
Yeah. So
Okay.
imagine the interconnects and
Yeah, right.
what's, I can't remember the term now, but the BGA where they melt the pins,
Right. Yeah.
yeah. Pretty cool
Okay.
stuff, but
There's
yeah.
something on the chip where they're basically doing a pin-like transfer between two different processes generating.
Right, because they may be using a 14 nanometer, which isn't 14 nanometer, process for the memory, layering that on top of a 6 nanometer, which isn't 6 nanometer process for the chip itself. So I don't know if you know this, but all those nanometer things are just made up.
Yeah.
It used to be years ago that those were actual measurements of either the gaps between the transistors or the transistors themselves.
Width of the wires.
But or whatever, right? But then they got to a certain point where they were just slightly refining the designs, and so they just made up smaller numbers to basically as a code name for that process.
When I was doing this at Azul, and we were talking to like Taiwan Silicon Manufacturing, so TSMC, they had their terminology, and it was different than Intel's terminology, but the numbers mapped to something, but the different companies were mapping them to different things.
Right.
So somebody was mapping them to the average wire width, and then the average transistor got smaller, and so they were mapping it to the average transistor, but your wires were everywhere and they were bigger. And somebody else mapped it to something else, the inner transistor space or fine. You know, there was a bunch of
And then there's only one company that actually makes the machines that they all use, which is that
ASML thing.
Netherlands or some AMSL. What is it again?
ASML.
Yeah, that's the one. Yeah. And
but back in the day with Azul, was known that long ago, TSMC was clearly manufacturing.
Yes,
so there's manufacturing, and then there's the machines that you manufacture.
Who makes the machines? Yeah. Oh yes, okay, fine. And it's ASML. Yeah, I can buy that. Yeah, fine. Yeah.
So and then there was that group in Texas that was funded by a combination of AMD and HP and Intel and others. I can't remember the name of it, but it was basically the US research organization that did all the oh shoot, does anyone know what I'm talking about? Arthur, anyone? It was basically funded by all the different chip companies to basically standardize the it was in Austin or Houston or
I would have thought I'd have known, but I don't know this one.
Can't remember. I'll look it up.
I mean, I lived in Houston, I got family in Houston, I lived in Austin, lived in Houston, I got family there. No, I don't know this one.
Yeah, well, the embarrassing thing is I actually worked there, so I should probably
okay, you beat my embarrassment.
I just hope there are some young people getting trained on all the lithography so it doesn't become a lost art.
Wait, don't you qualify as a young person?
Yeah, but I'm not doing chip lithography.
Oh, okay.
I'm sure they have like training processes. It's hard to learn this kind of stuff, even in grad school or anything like that, right? So you learn all of this little stuff on the job, probably.
This is like the guilds in the medieval ages. Okay, somebody makes, manufactures, and runs plastics plants, and all our lives depend on plastics every single day, every which way. But that is another arcane art. Hey, see you, Dan. That requires some real arcane knowledge to how to do these large-scale chemical processes.
Right, and how many people actually know how to do
that?
Just the ones working there.
About to say, yeah, I'm hoping, but yeah.
Yeah, because it's amazing, even in computer science, when I hire people out of college, I mean, they come in, they're like, yeah, I learned all this stuff at college, and they tell me all about it. And it's like, well, that's really cute, but none of that has actually been used in the software industry in 40 years. Like everything you learned at college, it's not that it's useless, it's just that it's not used. And there's a big difference. Like, they learn how to think in college, but none of those things actually get used.
I mean, there are some things that just take a long time.
Fresh out hires at a couple of companies is always very exciting.
We had structured programming and we were like, stop using go-tos. And it turns out the way we did that was teach the new people to not use go-tos and then wait for all the old programmers to die. And then we don't use go-tos anymore.
Wait a second.
You think more people switched?
I think that the go-to thing has fallen down to the
like 1968, Aaron. Come on, like when was Dijkstra's paper? That was 1968, I thought.
Yeah, I think so.
Decades before I was born.
All right, we're like in the rambling zone. I have a thing to be done on my new house.
Huh, it was 1968. Holy fuck. I
Yeah,
was
you
right
haven't
about something.
lost your brains. I knew that one. You're not senile yet, Cameron.
Not yet.
Not yet. Don't go there. Oh God, I'm going there, but I shouldn't be. Okay, what else? Got any questions here? I'm gonna aim for wrapping up here.
Just a super small one. So when you talk about like transistor count, you're not saying that it will use more transistors. You're saying it will be more complicated for like verification and all that, right? Or
Yeah, when you get into the L2 cache coherency protocols, it's some of the more complicated portions of a chip. Yes, so there's some amount of simplicity in terms of what the meaning of things are that you're going to deal with. And so, you know, having a game that says, I have a pending cache prefetch that is waiting for permission to fire off a certain number of clocks and then it fires anyhow. The engineer would just tell me, well, fuck it, I'll just delay it, or don't bother to issue it until you're sure, right? There's no help to get it out to the L2 and then wait. That defeats the whole purpose. So don't bother, go all the way to main memory, start it, or
okay. What you said makes sense. So I would need, if I wanted to do this, I would need to have a way to kill it within the core itself before you even.
Yeah, right. And at that point, you just don't issue it in the core.
Yeah.
Right. And then you lost because you didn't issue it in time in the first place.
Yeah.
Right?
The main purpose of the cache is to hide latency, but with the enlargements of the cache, I think the aim is now to cache the program's behavior. So somehow.
Yeah, there's large diminishing returns on these giant ass caches, but the distance to main memory didn't get any smaller, so you get something. I don't know.
Also, when you have more cores, you want to like reduce the interconnect load, and I mean, obviously, it's all very complicated. But
yeah. You add an interconnect because you want to have more cores, but on a different chip, you slow down main memory. Well, main memory is your main latency, so you had to win by having another core versus the loss you just ate. So for the long time, you've been able to buy single socket x86 motherboards that clearly had more performance than dual socket because you didn't have an interconnect. And when you went from dual to like 4 and 8 socket and you had to cross motherboards with connector cables and shit, you lost latency and you gained bandwidth. And then for some loads that works, and some loads that doesn't.
Right. And the big challenge back then with that giant discrepancy is that, you know, you had the 64 Sun CPUs running at 200 megahertz. And, you know, a single Pentium 4 was doing more more total instructions per second than the 64 of those put together. So
yeah, well,
programming language.
Last Sun round sucked really bad. They couldn't get it sorted out.
It was amazing technology.
Azul was doing better. We had enough cores that we could beat the damn x86, but you needed a bunch of them to beat one. It was an 8-to-1 ratio or 10-to-1.
Right, but instead of a PCI bus, you were over TCP/IP, which wasn't quite as.
I'm sorry, what? We were not TCP/IP.
The hardware basically looked like a NIC to the client-side JVM.
Yeah, but our programming languages have the concept of I'm talking across the network to someone else in the way that they don't have I'm on the same socket. I can't say I'm trying to break my process into 2 different threads, but please put them on the same core.
But sure, again, you can use Linux affinity and all that, right?
Yeah, people.
Right, my comment was my programming language doesn't really have that concept.
Yeah.
Right, because
it's not a programming language concept, right?
That's like programming languages are all based on a single CPU, a von Neumann machine. I mean, so it's hardly surprising that programming languages fight against us as we try to scale out throughput by adding cores.
So the Azul VM knew very well that it had lots of cores on different sockets, but the hardware model was that it was not NUMA, it was UMA, uniform memory access, but mediocre memory access latency, but uniform. So if you were on the same socket, you had some little tiny gain, but if you were cross socket this way or that way, it was all the same. So it didn't really matter. We just fire, but it was important to fire off more threads. Bandwidth to spare, CPUs to spare, fire off threads.
So the horizon is we are getting more CPUs. It's not.
Yes.
Yeah.
The universe is parallel. Welcome to the universe.
Although that's already started slowing down pretty dramatically in terms of the growth of cores. Last 2 generations were maxed out at 64 cores in a socket.
Because no one knows how to use them.
No one knows how to use them.
I wouldn't say that that's the reason. So many like modern deployments, you don't have a single program spanning the whole thing. You have like little like mini Linux processes. So you don't have to actually like code to the whole machine.
Right. People change their model from parallel shared memory to parallel not shared memory, which is cloud. And they added the model that says I'll tolerate some amount of failures at some amount of cost. And now I want as many cheap and fragile, unreliable nodes as I can get. And I'll make the ones that manage to survive long enough do some useful work. But if nodes die on me, I don't really care. I won't be dead. I'll carry on.
And eventually you'll run out of like memory bandwidth or network bandwidth or whatever. So adding more cores doesn't necessarily.
Well, the Azul answer showed that you could just add bandwidth to your heart's content. We could get stupid bandwidth. But it wasn't the cheapest because everything had to work perfect or you lost the whole unit. Whereas the Google solution was, I'll just throw another box in the data center, another box, another box, another box, another box. Latency between nodes sucks, it's big. Nodes are fast and unreliable and they fail and I don't care. I'll just redo the computation in the small on the one failed guy. Making that all work was a kind of a pain in the neck, but once it worked, you have same as RAID gave you redundant array of inexpensive disks as a fast way to get parallel disk throughput. You got redundant array of H2O as our starting point. Redundant array of inexpensive nodes, but it's a cloud-based node solution where you just threw more nodes in. But then you had the cluster controller, you had Kubernetes comes along, you got whatever name node and Hadoop, and there was a software model that began to arise that lets you compute at that scale. And for very large data sets, it works. The H2O solution somewhere in the middle. We get a lot more throughput per node than a Hadoop-like cluster or Google-like cluster. We have scaling issues at the petabyte level based on reliability issues. At terabyte level, it worked great. Fine. All right. Yeah, I'm getting poked at by my wife. I need to wrap it up. We have a deal with the realtor in the house, and there's a lot of deals floating around, and all of them have to be done. We're in the hurry up and wait zone, so we got to hurry up, and then we're going to wait for a week, and we're going to hurry up, and then we're going to wait for a week, and then we'll be moving, and then we hurry up or we load, and then we got to get out of the house, and then we got to wait for tradespeople to come clean this place up.
Make sure you order your Starlink well in advance.
Yeah, a Comcast cable. We're not so far out in the woods. We get Comcast cable, so I'm okay on that front. But we got septic system. We got gas in a tank beside the house. Solar power, whole house generator, water from a well. The modern version of living in the woods, mountains. Yeah. All right. Until next time.
Okay.
Bye.
Bye.
All right. Thanks.